benchmark completed correctly, right? Very surprising. Basically, we threw away code from Apache, and it still performed its task. That tells you there's a lot of redundant code in there. But it also tells us that there's a lot of code, or rather that programmers write defensive enough code, but don't catch all possible exceptions that may occur, right, such as buffer overflow. So if we can catch them somehow, and we can convert them into these inline error return codes, then there's a high probability that the program is going to behave correctly. Well, for some confidence of correctly. So now, of the 15 functions that caused the crash when we did this fault injection, 10 of them, in fact, were in the startup phase of the program. So in fact, we should discount them because we don't really care about failures that occur there. They're not affected directly by input from the network. So we'd never actually get to fix software in those cases. But it's a matter of semantics. For SSHD and bind, same type of statistics. Near 90% of the functions that were active, we could do fault injection, and the program would keep running and keep serving subsequent requests. Very surprising result. So again, this points back to this idea of well-behavedness of code, and that programmers may not be as incompetent as we've made them out to be. And there's some independent work that confirms this hypothesis that I won't go into due to time considerations. But there's some work at OSDI last year and at microarchitecture last year or the year before that shows that software is in fact quite a bit elastic. You can abuse it in certain directions along certain axes, and it'll behave in nice ways. But if you abuse it in different ways, it's going to crash. So, getting back to how do we enable self-healing software, basically the idea is think of the previous sort of four-step feedback loop. Now what we need to do is put lightweight sensors around the software that we need to make self-healing. And then once we detect a failure, we need to have enough of a logic component that we can recognize the type of attack, which basically the sensor is going to tell us what it was, and also localize it in terms of where it happened in the code. And once that happens, we can use microspeculation and error virtualization to apply a fix around that piece of code such that future instances of that failure in that piece of code are going to be treated according to what I've told you so far. And then this may lead to more than one possible fixes. And we can test each one of those and see whether they work by feeding them the input vector that caused the failure to begin with, and perhaps running some regression testing, some functionality testing, and see what happens to it, if there are any side effects. If we're happy, we can go ahead and deploy it, or we can wait for the administrator to click the deploy, or there are all sorts of strategies. But in principle, this whole thing can happen automatically. So the first case study is what we call the worm vaccine that targeted the problem of network worms using buffer overflow attacks. As I said, proof of concept, we don't really care much about buffer overflows, but they're a nice type of failure that people are interested in. And it has the other nice side effect that it's easily recognizable if you know what you're looking for. And also the network servers are transactional in nature, so we can easily replay input to them and see what the impact of that input is, right? So we're creating an easy system to test. So basically, we take a production server, we instrument this server in a separate environment, whether it's a virtual machine or a completely different system, and we put some logic that does the identification of the fault and try to localize where the fault happened in terms of this routine. This is where it happened, right? This was the call trace, and create instances of this, test, and so on and so forth. And now we have several possibilities as to how we actually trigger this analysis. We can either wait for the attacker. I don't have a laser pointer. We can either wait for the attacker to directly attack the system. So this would be a honeypot-like version of the system, or we can put some type of anomaly detection at the end host or at the firewall, the router, that creates hints or suspicions that a particular request, a particular piece of traffic, sequence of packets may be anomalous. We don't need to know for sure. We just need to create suspicions, right? And then we can test these suspicions in the analysis environment. So going from the simple block diagrams to once we fix it, we update the production server if we fix it, of course. And this is what the full architecture looks like. But moving on. So how do we create these sensors? How do we create this analysis environment? In this system, we use source-to-source code transformations to. Excuse me. We use source-to-source code transformation to wrap all memory references, all accesses to buffers, that could potentially be susceptible to buffer overflow, and store enough information as the program runs to keep track of where it is executing at any given time. So when the program detects a buffer overflow, it emits all the information saying, hey, here's where I was executing, here's the buffer, here's the function, everything we need. And then we wait until an attack hits. One point here is that we can actually use any type of protection mechanism as an oracle, but we decided to use this approach because it's more efficient. So the example that I gave earlier gets transformed to this example. It doesn't really matter. It just keeps track. The parts of the code in red is what the system injects. And basically, it uses a technique similar to electric fence to wrap buffers around memory protected with write protected memory pages that are zero filled. So overflows, underflows are going to create exceptions. Okay, 5 minutes. And so on and so forth. You can go through the slides later. Very simple technique. And the idea is that the same type of technique can be applied on the as a fix, in this case, where we save the state of the program right where it says set jump before the piece of code that we know is vulnerable, we detected in the past, string copy, and then if a fault does occur, we recover to it by skip execution. And in fact, in this case, the semantics are the same as if the programmer knew how to do array bounds checking. Both. All right. So once we create such fixes, we test them with all sorts of bad input, good input, all the things, and then if we're happy, we can deploy. Does it work? Yep. We had 80-something percent success rate against known, well, to us, vulnerabilities against real open source software that we put in the system. We hit it with it, created patches that actually addressed the problem and kept the application running as well. And we could possibly do better. It took 60 seconds to do this for Apache, which is the biggest program that we had. I'll skip the performance because it works. Here's a system view of the web-based front end that can control the system. So we have a number of systems here, and we can launch an attack against them if we want. This shows what happens, the steps that the system goes through. Detect an attack, patch, generation, compile, test, pre-deploy. At pre-deploy, if the configuration may be that stay here until the administrator says go ahead and deploy. Of course, a patch may fail in the testing phase or the generation phase, and this is what the patch looks like because we operate in fully pre-processed source code. But if you look at the grayed out areas later on, I'll send the URL. You can see that the fixes are similar to what I posted earlier with the red lines on the code. And database of all sorts of failures. I'll skip the observations because they're fairly obvious. And now the problem with this is that it depends on the code that is compromised, that is wrapped around to not have any kind of failures, not have any kind of external memory references. So instead, we want to keep track of all memory references and do real recover, unroll as for the string copy or the piece of code that we've seen fail. And we'd like to operate in a binary-only environment, not require access to the source code as in this system. So we've built STEM, which stands for Selective Transactional Emulation, where we basically implement microspeculation and error virtualization by emulating just parts of a program as it's executing, and the rest of the program runs on the native CPU. And for the part of the program that's executing, you keep track of memory changes. And if anything bad happens, we unroll it and do error virtualization. Right. So otherwise,